Hi, this is Valeria, and I'm presenting the second example. In my last video, I forgot to talk about the pertinence of the Ferris wheel to Evanston. The Ferris wheel I modeled was specifically the one in Navy Pier. The Navy Pier in Chicago greatly influenced Evanston's culture and entertainment. Lake Michigan is another influential force. The next example models the height of the tide of Lake Michigan at X hours. An important equation to keep in mind in solving this problem is the general equation for cosine waves, which is the same as the general equation for sine waves. Y equals A cosine bx minus h plus k. I talked about the significance of these variables in the first video. The following information that I'm about to tell you about the high tide height time and the low tide height time I found in ChicagoWeatherCenter.com, and they represent one day in particular. For the sake of the problem, they're going to act as the average. Here they are. The high tide was 2.7 inches and it happened at 10:27, and the low tide height was 0.4 inches and it happened at 17:07. I'm going to draw a diagram so we can orient the picture visually. The x-axis represents the time and the y-axis represents the height of the tide. So now we will graph these 2 points. So 10:27 is the time, meets up with 2.7 inches around here, and the time of 17:07 meets up with the 0.4 inches here. And right here they form part of a cosine wave. Now we need to find all of these variables so we can fill in the general equation. First of all, the axis of wave, which is the line that splits the graph in two, is y equals 1.55. Goes around here. You get this by taking the average of the high tide height and the low tide height. 2.7 minus 0.4, 2.7 plus 0.4 divided by 2, which gives you 1.55. Next, we want to find the amplitude. The amplitude is 1.15. We know this because we need to take the distance from the highest point to the axis of wave, and we do that by subtracting 2.7 minus 1.55. That gives us 1.15. The amplitude is always half of the total height of the graph. The next point is the period. And to get the period, we need to find the distance from that distance that occurs in one cycle, which would be this area. We do this by doing the high tide time minus the low tide height time times 2. That would be 2 times 17 and 7/60, which is the same thing as 17.07, minus 10 and 27/60, which is the same thing as 10/27, and that will give us 13 and 1/3. We times this value by 2 because we want one complete cycle, and if we were to just subtract 17.07 by 10/27, that would give us half of the period. Now that we have these points, we need to figure out the shifts of the graph. The original cosine graph goes like this. And this graph, you see that it's shifted. We know that it shifts up and to the right. It shifts to the right 10 and 27/60. This is our highest point at 10 and 27/60, and originally it was at 1, so it needs to shift that way. We also need to shift it up 1.55. We know that it's at 1.55 because for the parent graph, the graph of y equals cosine of x, the axis of wave is at y equals 0, but for our current graph, it's at y equals 1.55. Now we can fill in all of our values. We have y equals 1.15, the amplitude, times the cosine of b, and we know what b is because we know that 2 pi over b equals p. We have 2 pi, we do not have b, but we do have the period, which is 13 and 1/3. So now we solve this equation to get b. 2 pi equals 13 and 1/3 times b, and we divide that by 13 and 1/3, and b is 2 pi over 13 and 1/3. This b goes right here. 2 pi over 13 and 1/3. Then we have x minus 10 and 27/60, which represents the shift to the right, plus 1.55, the movement upwards. And this right here is our cosine function.